Welcome back to our third and final video in this series, in which we introduce you to the actuator, the computer that writes its own code. In this video, we're going to show you the actuator in action. In our first two videos, we reviewed the problems plaguing software development today. It's expensive, error-prone, takes too long, and rarely does what it should. We've also seen that despite recent improvements in large language models, experts know that they will never be good enough to write complex, accurate code. The previous video introduced our visual invert structures and showed how they replace the need for pseudocode. They make it possible for a non-techie to specify exactly what they want in precise detail without any need for logic. They're easy to understand and easy to edit. And since the invert structures also serve as your documentation, they're always up to date. In practice, this means that we've found a way that smart non-techie people can specify software of great sophistication without needing to have a background in coding. We have strong guardrails in place to stop you from introducing inadvertent errors to the actuator, and because you're able to precisely specify everything all the way down to the tiniest detail, miscommunication will soon be a thing of the past. If we were to stop right here, we could declare our mission a rousing success. Inverts can substantially streamline the specification process, using a smaller team, minimal project management, much less back and forth, much less time, and nothing deferred to a later phase. Indeed, for many applications, the specifications can now be done by a single person. This means that if a programmer could take an invert structure and write the corresponding software code, we'd be well ahead of the game. But we're not going to stop there. I'm sure you can guess what comes next. Yes, we have built a computer that can take these invert structures and build robust, accurate code from scratch. She's been trained to analyze any of the unlimited number of possible invert structures and build the code that she then executes, right in front of your eyes. She uses artificial intelligence, but not one that is based on simple pattern recognition used by current AI models. In essence, she's been taught how to think. Let me show you what she can do. I'm going to show you some simple examples that illustrate what the actuator can do. We're not going to read or write to databases or do any complex random models. We're just going to focus on some things that are easier to validate. Any coders out there will recognize that the first couple are fairly straightforward to code, but others will be a bit more of a handful. I invite you to think about how you might actually code them yourself. The first one deals with text. You can see by the name that we're going to insert one piece of text into the word abracadabra after we first convert it to lowercase. We'll insert it into the position given here as the highest common factor of two numbers, 30 and 85, which of course is 5. We'll insert some text UVWXYZ, in which any occurrence of UV has first been replaced with another piece of text here. Here we take A, B, C, D, E, F, G, H, I, J and strip out the first three letters. Then we're going to take the resulting D, E, F, G, H, I, J and remove the characters starting from position 4 and ending in the position given by the remainder from dividing 47 by 7. So we're removing from position 4 to 5, leaving us with D, E, F, I, J. So now, D, E, F, I, J replaces the UV in UVWXYZ, giving us D, E, F, I, J, WXYZ. This is what we insert into position 5 of abracadabra. And here we see the answer. Let's change a few things to see what we get. Instead of a remainder of 47 from 7, let's use the fourth lowest element of the array 928376. Our answer is now a little different. Instead of abracadabra, let's just concatenate X, Y, Z, A, B, C, M, N, O, R, S, T. Each time the actuator figures out from the invert structure what it needs to do, builds its code and executes it. Incidentally, you can see here how easy it is to open and close these things. Let's look at something with a few numbers. It also shows you some intermediate values so you can follow along. Here, we want the maximum of 3 different numbers. The first one is the double factorial of 4. In other words, 4 times 2 equals 8. Quantity 2 is a little trickier. It's e to the power x, where x is given as an average of 3 numbers. The first one is just the number 5. The second one is the present value of an annuity immediate, payable monthly for 7 years at an interest rate of 6%. Here's what it evaluates to. The third one is a trigonometry measure, the cosec of 60 degrees. And there's your answer. Try to validate it for yourself. Incidentally, the blue label indicates that I can add additional elements to this average. So let's just insert the array product that simply gives you the product of all elements in an array. Here, you can see that the product of 0.1, 17, 5 and 18 is equal to 153. There's no limit to the amount of messing around we can do here, or how deep we want to take the structure. For this next example, we'll look at sequences. We're going to append one sequence to another, and then we'll append that to the array 77, 88, 99. The first sequence is derived by extending from another sequence, by adding 3 elements that grow arithmetically from the end. That target sequence is an autoregressive sequence with 5 elements, that starts with 1, and each subsequent element is double the prior element. So clearly, we're going to get 1, 2, 4, 8, 16, and then extend from the 8 and 16 to get the elements 24, 32, 40. For our second sequence, we're going to take incremental differences from the sequence 1, 5, 2, 8, 6, 4, which gives us 4, minus 3, 6, minus 2, minus 2. And there's our answer. Finally, we'll replace this sequence with one that represents the highest 4 consecutive elements from the sequence 3, 6, 6, 4, 7, 2, 9, 2. You can see that this is 6, 6, 4, 7. And there's your answer. Any programmer watching this will appreciate that some of these variations can be a little tricky to code. This next example shows some manipulation of sets. We're going to take the set of numbers 1, 3, 5, 7, 9, 11, 13, 12, 10, 8, 6, 4, 2, indicated here as sample set 5. We're going to sort it. Then, we're going to select any elements that are in a position that is a multiple of 2 or 3. And here's your answer. Next, we'll change the 2 to a 5. And here's the answer. Finally, let's convert the answer into deciles. And here's the answer. We've just seen the first ever computer to build complex code quickly and accurately. We've seen this for a variety of different invert structures across a number of technical domains. We've tested the actuator's ability to build software using any of the 1100 inverts in any combination, no matter how large or complex. I'm sure by now you have some burning questions. Does she write the same instructions every time? Yes, the inverts specify exactly what you want, and her code represents exactly what the inverts are specifying. There's no room for ambiguity. What can the actuator be used for? The actuator can write code for anything that can be expressed as a combination of inverts, no matter how complex and large. She really comes into her own with software that 1 is very complex, 2 must be developed in a hurry, 3 is subject to regular modification, perhaps due to product iteration, regulatory change or modelling, or 4 requires precise, accurate specifications, such as financial applications. Because of her transparency and robustness, she is ideally suited for systems of critical importance, for which a crash would have catastrophic consequences. She can also be used to troubleshoot existing legacy software, and to make sure it really is doing what it's supposed to. Here, the advantages over traditional hand-built software are overwhelming. How fast is she? In terms of the overall development process, the actuator is orders of magnitudes faster than if you had to use software engineers to write code by hand. A typical software project that might take several coders 6 months can be built by the actuator in less than a second. In terms of execution speed, the picture is less clear. In certain areas, we've developed innovations that significantly speed up execution. In other areas, she runs a little slower due to the controls added to prevent software errors. We think the trade-off is well worth it. What makes the actuator bulletproof? The actuator eliminates practically all of the errors commonly seen in hand-coded software. In a previous video, we showed how the Invert builder's checks and guardrails catch any inadvertent data entry errors that could be introduced by humans. Similar checks are made of any data arising from an internal calculation or from an external file or database. Where necessary, the error is flagged and appropriate defaults are applied. Because the actuator is a machine, she always produces the exact same instructions for a given invert structure. This means that once she knows how something works, for example sorting numbers in a row of a table, she does it the same way every time. She does this for every single piece of software she generates. This means that each potential error only had to be fixed once. Contrast this with a human coder who repeats prior errors every time they write new code. That just leaves mistakes that we might make ourselves. We have gone to extraordinary lengths to teach the actuator clean, efficient code and to systematically test her logic and thinking patterns. This was a huge task for us, but something we've only had to do once. A more comprehensive set of FAQs dealing with every aspect of this can be found on our website, Ac28R.com. In video 1, we talked about the shortcomings in current software development practices, and we made some strong claims about fixing them. Let's see how we did. Software coding time slashed down to seconds. Practically bulletproof. No more misunderstandings. Get it right the first time. Technical expertise no longer necessary. And future modifications without pain, as many times as you like. So what will change for you? No more missed deadlines or cost overruns. You know exactly what you're getting the moment you put your inverts together. No more debugging and testing. Your best software engineers will be freed from coding drudgery to do more satisfying high-level work. No more embarrassing and costly software crashes. No more sleepless nights. Happy customers, happy management, happy employees. Your flexibility and speed will be transformed. This will allow you more time to focus on your core business. Documentation finally becomes something that you can trust in. The invert structure corresponds exactly to the underlying software that the actuator creates. And since the inverts are so clear and easy to understand, they serve as perfect documentation for the future. So what's ahead? In the near future, we hope to release further videos that demonstrate the actuator's capabilities in more depth. We also hope to conduct interactive demonstrations to allow for questions and to gather feedback. We've reached the end of this 3-part series. We don't have to tell you that the implications of this are staggering. We've shown you a completely different approach to specifying software, and this has laid the ground for teaching a computer to write its own code that doesn't need to be checked by a human. You've seen that the actuator eliminates the shortcomings of today's handcrafted software. It should be clear that AI tools based on large language models cannot write reliable code to any level of precision and will never get there. The best they can ever be is a coding assistant. The actuator isn't just a coding assistant, she is the coder. We hope you found this interesting. If so, please consider sharing it. If you have further questions, you can also find more details as well as extensive FAQs on our website, Ac28R.com. Until next time.